Do you have any questions from the previous lectures?
Yes, sir.
You can ask it.
Yes, sir. I was preparing for the assignment and I for the flower classification recognition. Image classification using CNN as a feature extractor.
Well, your voice is not clear. Can you repeat your question?
Yes, sir. I was saying that in the image classification using CNN as a feature extractor,
Mm-hmm.
sir, you use the net. Sorry, yes, the net which was the ResNet 50.
ResNet 50, yes.
Yes. So, sir, you first demonstrated the net layer 1 and the net layer, the end net layer, which was the classifier. And after that, you plotted the CNN architecture of the ResNet 50 in your video. Yes.
Okay.
So, sir, I also tried the exact same program with the VGG16, but it did not show the CNN architecture of the VGG16.
Did you download the pre-trained model for VGG16 first?
Yes, sir, I did.
So let me share my screen.
Yes, I have run the whole program to VGG16 and I obtained the accuracy, but it was not showing the CNN architecture through layer by layer, which shows the two branches, the whole CNN architecture. Net is divided into.
That part is only for show you the architecture of the ResNet. It is not related to the project. Only I want to show you that there are several layers in the ResNet. So I display them in a one figure by using some command to show you that we have several layers, but in using CNN as a feature extractor, you only need to know the name of the layer that you want to use it as a feature extractor. So for example, here I use GoogleNet. I load the GoogleNet first. I want to let me run it. I want to select one of the layers of GoogleNet as the feature extractor. So I need to know the name. So you can use net point layers to find out the name of the layers here. And generally we use layers near to the last layer as the feature extractor. For example, this fully connected, which the name is last three classifier. It's a good candidate for selecting as a feature extractor. So when we select this layer and its activation function will be selected for the feature extraction, for each image we will have a feature vector with 1000 entry. So it doesn't necessary to display this GoogleNet shape on the screen. We need only know the name of the layer. So you can select any other layer. For example, maybe someone want to check the this layer as a feature extractor. So the size of the feature in this layer is 128 multiplied by 3 multiplied by 3 multiplied by 96. So it's a very huge feature vector. But the last layer that I show you, the size of the feature vector will be 1000 for each image. And the features that can be extracted by the last layer, of course, will be the most complex and most powerful features in most of the cases. Okay?
Yes, sir. It does not matter we use the plot function or
No, not necessary. But you have to select different architectures. As I show you in the previous video, there are a lot of pre-trained model in MATLAB. You can download them and use them as the feature extractor. We use ResNet 50. There are other ResNet 101, ResNet 18, Inception, Exception, VGG16, AlexNet. So each of these architectures can be loaded, and then you should check the name of the layers and select one of the layer activations as the feature extractor in your project, and train your model, your SVM model, and uh, find the accuracy of the system and report it in your project report.
yes. So I did the resonant 50 with the and compared that with the VGG16. So VGG16 was almost 77%. The resonant 50 was 82. So it's better.
Yes, of course. These advanced architecture, we expected to get better results with them, and maybe, as you can see here, uh, these architectures we expect to uh, find better results with them. Exception, DenseNet, Inception, NASNet. These are maybe better candidate for using as the feature extractor. But it depends on the nature of the dataset also. We cannot say that in every dataset for example, VGG16 result will be lower than the exception. But in most of the cases, we get better result from the exception. Also, it is faster. It is smaller, but this one is faster. So there are some advantages and disadvantages from using different architectures.
Then the confusion matrix, you were
There are some command in MATLAB for drawing or plotting the confusion matrix. Plot confusion, the target label and the truth label actually, and the predicted label. We can give it to the plot confusion, and it will display something like this: the output class and the target class. So what was your problem? What was your question?
can you open the YouTube video, and from there we can see the confusion matrix command, the last command.
I don't know what happened to my connection. Some sites cannot be opened. I don't know. I have the problem with the Teams in the beginning. Now I cannot open my YouTube. What about Gmail. Gmail is working. So will be solved with that one. But in the confusion matrix, we have truth label and predicted label. So for example, now we have in this example 10 classes, and these are the predicted label of for these 10 classes. And as you can see, for example here 9.5% of the images or samples that are belongs to class 9 correctly classified as 9, but the other ones are classified as the wrong class or misclassified in fact. So but maybe this is not the value of the misclassification. I should check the output. Here we can see it better. This is the output class and this is the target class. 446 samples are belongs to class 1 and classified as class 1. Also 236 samples belongs to class 2 and classified as class 2, but 12 samples belongs to class 1 but predicted as belongs to class 2. So this is misclassification, and here 5 samples belongs to actual class was 2 but the predicted is 1. So this is the accuracy, and the other numbers are the false accept rate, false reject rate. As you know, we have precision, recall, and some other metrics that can be extracted from the confusion matrix. Accuracy is one of them. Precision and recall also can be extracted for each of the classes. Okay, let me start the new lecture. Today I want to show you two problems. First one is classifying the images inside one of the famous dataset, CIFAR10. Let's see the CIFAR10 website. As you can see, it's a data set contains of millions of tiny images. There are two versions, CIFAR10 and CIFAR100. In this one we have only 10 categories, and in this one we have 100 categories. And as you can see, it contains several, in fact 60,000 tiny image, 32 pixels by 32 pixels from 10 classes: airplane, automobile, bird, cat, deer, dog, frog, horse, sheep, and truck. And as you can see, images are taken in wild, so there are a lot of background and other things in the images, and the images are taken in different position. So it is one of the famous data sets that are used in machine learning and deep learning. today I want to select some of them and train a model from the scratch. So first you have to download this data set from this link, CIFAR10 MATLAB version. Then by using this MATLAB script we can extract the this MATLAB script download, and let me see, is it download? Downloading, and also extracting the images from the data set, because when you download it, let me show you the type of the data set. CNN sources data set. Okay, this is the data set that I download. If you open it, it contains some MATLAB matrix only, so you cannot display them or see them in the windows, but by using this script the images will be extracted and stored in two different folders, training and test. If you run this script you will see some output like this one, CIFAR10 test and CIFAR10 train. If you open them, there are 10 subfolders. These are the images of airplane class. 5,000 tiny images from airplane, different type, for example bird, and the other ones. So after you download the dataset and run that script to create CIFAR test and CIFAR train, let's see how many images we have here. 1,000 for each class we have for train test, and 5,000 for train. We have 10 categories, so 50,000 images will be used for train a model and 10,000 will be used for test if we use all of the classes. But in this example I only want to select these 4 classes: deer, dog, frog and cat. So you can use all of them, or you can change this line and select some other categories, add it or increase it or decrease it. So let's run the program till this point. So I load the image data store, and this is the training set. Since the previous script divided the images into training and testing, I don't need to split the images by MATLAB function. All of the images in this IMDS are the training set. In this part I declare some layers. You can declare them inside the CNN architecture, or you can define them outside and give them some name and use that name inside your architecture. For example, convolutional 1 is a two-dimensional convolutional layer, and this is the size of the input image. It's a 32 by 32. So if your image is a square shape, you don't need to mention 32 inside a bracket. One value is enough. So this is the 32 by 32 image, and this is the number of filters, and the padding 2 means that put 2 row and columns of 0 around the images, and bias learning learn rate factor is 2. Another learning parameters to enforce this layer to learn more features. It is not important. Fully connected layer FC1 and FC2 are also declared here. The first one has 64 neurons and the second one has only 4 neurons. This is the output layer, and the number of neurons should be exactly the same as the number of classes that we have in this project. In this project we only focus on 4 categories, so you can see there is a 4 here. So in the line 14 we start declaring the CNN layer. Till this point the first layer is image input layer, 32 by 32, and we have 3 channels because the images are RGB, red, green and blue. Then the first convolutional layer is here, max pooling with kernel size 3 by 3 and stride 2. In the previous example we only use max pooling with 2 by 2. Now this max pooling select the maximum of a pixel inside a 9 pixels neighborhood and put it in the result for output. Then the filter will be moved 2 pixels to the right, and this operation will be repeated. This is the non-linearity rectified linear unit layer, and again we use convolutional 2D layers, extract more features. In this example, for the second convolutional layer I use a filter 5 by 5. We extract 32 features, and after rectified linear we perform average pooling. The third convolutional layer, again the filter size is 5 by 5, and now we extract 64 features. And okay, here we use average pooling. Another type of the pooling is average pooling. In max pooling, inside the neighborhood we select the pixel or feature with the highest value, but in the average pooling the average of the values inside this 3 by 3 neighborhood will be computed and will be put inside the output result. In the last layer, before we perform the classification, we put one fully connected layer and one rectified layer again, and the output which contains 4 neurons. We perform softmax layer and classification over the result of this fully connected 2. So let me run the program till this point. Here we declare the training options, the learning rate. It is possible to have different learning rate in different uh, situation of the training, different point of the training process. It is better to use high learning rate in the beginning and decrease it after a while. So as you can see here, initial learning rate is 001, and we use learning rate schedule piecewise, so after a while it will be dropped by 0.1. so after uh, 8 iteration, learning rate drop period is 8. After each 8 iteration, the learning rate will be dropped by 0.1. These are another learning parameters. L2 regulation. This is the maximum number of epochs, and this is the batch size. We use 100. So in each iteration, 100 images will be given to the system. Okay. In this line, we start training the model by using this image inside this image data store, the layer that I declared, and the options that are declared here. This is the 15 layers CNN architecture, and this is the 20,000 images inside the 4 categories. Okay, let me run it till this point. Takes some time, so you can ask a question.
Yes, sir. We are using this CIFAR10 dataset for image recognition by
Image classification, yes.
image classification by any. We can use any data. Network, pre-trained network.
Sorry, what was your question?
I'm saying, can we use any pre-trained network?
Yes, of course. In this example, I want to show you an example of training a network from scratch by declaring different layers, but you can use pre-trained model. But for this example, since the size of the images are very small and all of the pre-trained model that we have needs an image with size 224 by 224 or something similar to that one. So if you want to import these images inside that model, you have to zoom your image, and there isn't any quality. Let me show you. For example, if I want to open this image, if you want to feed it to your CNN, you should change its size to 224 by 224 or something similar to that number. So as you can see, the quality of the images are very low, so we can test it to see is it can we get better result by using a pre-trained model, or this simple architecture that I declared here is enough? So here we are in the epoch 1 iteration 1, 50 and 100, and these are the accuracy till this point. As you can see, for now the learning rate is 0.001. After a while it will be dropped by 0.1 and the learning rate will be decreased. So we use learning rate schedule and we use piecewise method, so after a while it will be dropped. I think this learning rate drop period is shows the epoch, not iteration. Of course, it's epoch. After 8 epoch, the learning rate will be dropped. But now we are in the first epoch, and it seems that it takes more than, for each 50 iterations we need approximately 2 minutes. So I think it is not possible to finish this learning. I will record the complete video about it and put it in the YouTube. Okay, here let me continue the explaining the code. This is the path of the test set. We have terrain set and test set. After you run the script that I mentioned, this is the path of terrain test, and this is the path of test set. So I load the data set, terrain set, test set, sorry, and also I get the truth label, sorry, the prediction label by using classify function. So after we train the model here in this line, we use it to classify the images inside the test set, and as the output for each image the classify function gives us a prediction label. Now I should check it, is it correct or not. Before that I wrote some code here to show you some samples. So if you run this part of the code several times inside your command windows, we select randomly one image from the test set and then we display it on the screen. Also I give it one label. The label will be displayed in green if it is correctly classified. Otherwise the label will be displayed in red. So we show the actually till this point by this lines. If you run it in this command window, each time that you copy paste and run it, you will see what we select randomly one images, and then you can see is it correctly classified or not. If it is correctly classified, you will see the label as a green. Otherwise you will see the wrong label for that image in red. This is the part that we select red or green if the label of this image is equal to the truth label. But also here I show you the confusion matrix and the mean of the confusion matrix is, or mean of the diagonal elements of the confusion matrix is the accuracy. So I display the accuracy of the system in the end. We are still in epoch 3. Till now the mini batch accuracy is 63. So as you can see, it is increased every time. Sometimes it is dropped, but in most of the case it is increased. So it means that we are successfully training the model. I remember that when I run it on my system, it takes approximately 30 to 40 minutes, so we cannot continue it here, but I will record a video about it and show you the total process. But after we finish that part, you should run this part of the code, classify the test set by using the train model, and get the prediction label. Then this prediction label and the truth label can give us the confusion matrix, and as I mentioned, you can give it to the this plot confusion. Plot confusion takes two arguments, target labels and output labels. So here you can put plot confusion. Let me copy paste it. This is the truth label, and this is the label that we achieved from the classifying. So from the classifier. This is the prediction labels. So when you run this part, you will see some graphical confusion matrix, something like this, and also you can see the precision recall value for different classes. In our example, we have 4 classes, so it will be a 4 by 4, and then we have one line here, one column here, so we have a 5 by 5 shape. Okay, this is one example, but also, as your friend said, we can test this system and this data set by using a pre-trained model. Maybe I ask you to do this type of manipulation in your midterm exam. So you can play with these architectures and check the accuracy of different models. But let me stop it.
Sir, will you share this whole code?
Yes, of course, I will share it.
Okay. Thank you.
Also, as I mentioned, there is another code that you should run it, and also you have to download the CIFAR uh, CIFAR10 from the website and put it in the same folder which these M file or scripts are exist there. Okay, as you can see, the training is completed after 10 epochs, and as you can see from this epoch number 9, the learning rate dropped by 0.1, and the final accuracy of the system is 72.88%. Also, I display the confusion matrix. So these are the output class that are produced by the model, and these are the truth label. We have 4 classes. So for the frog, the classification accuracy is 81%. For dog, it is 68%. For the deer, it is 77%, and for cat, it is 62%. So the second number in this square is the misclassification, and this is the correct classification rate. This is the number of samples that are correctly classified as cat, and these are the number of samples that are misclassified, 69. This is the output class. The actual class is cat, and it is classified as cat. This is the cat that is classified as deer. This is the dog that are classified as 243. Cats are classified as dog. So 88 images are belongs to cat categories, but they are classified as frog. Let me show you some of them. As I mentioned, if we copy this part of the code, one random sample will be selected, and we choose all of the figures around again. So this is something similar to cat, but the system misrecognized it. Let me run another one. And this is a cat figure, and the system classified correctly, so the label displayed in the green. This is a frog, and the system classified correctly. This is another frog, correctly classified. This is a deer. This is a deer, but the system considers as dog. This is a cat, I think, but the system considers it as frog. But the resolution of images are very low, so it is very hard even for human to classify them. Okay, let me give you another example. In this example, I want to perform some regression over the actually I want to design a model in order to predict the necessary rotation angle for some numbers. Let me show you what we have here. Okay, I clear everything from the workspace. This data set is stored in a 4-dimensional array. So let's see what we have in this data set. We have X terrain and Y terrain, X validation and Y validation by calling these two functions or these two modules. And as you can see, the X terrain is a 4-dimensional array. Let's see what we have inside the X terrain. For example, X terrain column 1 is the first item in the terrain set, and it contains some numbers between 0 and 1 because it's a grayscale image. Let me display it, maybe it's better to see it. I am show so as you can see, there is a small handwritten digit in this example at number 3, and it has some it is not aligned. It should be rotated, for example, in the right side in order to show a aligned number 3. Here inside the data set, for each of these samples they provide the necessary rotation angle. For example, for this one, inside the Y terrain, let's see, Y terrain is the 5000 by 1 vector. So let me see what we have inside this one. Y terrain index 1 minus 42. It means that this image should be rotated 42 degrees in this direction, in the clockwise direction, 42 degrees, in order to make it aligned, and we can see a tree on the screen. Let me bring the part that we can use it. For example, in MATLAB we have a function to rotate an image. I am rotate. The input is x terrain index 1, and the angle that I want to rotate is inside the y terrain. It is provided for us, and this is the bicubic crop, the method that they use for rotating and find the interpoint values. And then there will be some black area around the image. We want to crop them, so I will put it inside images rotated, for example. Now let me show you what will be the result after rotating this image. Figure I am show image rotated. What is this name? Image. So as you can see, when I rotate this image, (42° in the clockwise direction, the tree is aligned. So for all of the samples that I have in this data set, they provide the rotation angle in order to align the images. Now I want to create a model which predicts the necessary rotation angle for test set for the unknown or unseen images. So as the input, I will give it some training samples, some images, and also instead of label, here we give them some value. So instead of classification, we have regression problem. Let's see. Regression or regression.
Regression.
Regression. Okay. We have regression problem here. So the output of the system will be a number, a value between, in this example, -90 to +19, the rotation angle that we need. But in the other example that we solved to this point of the course, we perform classification. The output is a predicted label, but in this example the output will be a number, and the system said that if you rotate this image by this number, the image should be uh, correctly rotated. Let's see how we can do it. Do you have any questions till this point? Are you here?
No, sir. No question until.
Okay. So this is one example of regression. It will be very similar to the classification, only a small difference. So till this point we only load the data, X terrain, and the correct rotation in the Y terrain. X validation is the test samples, and Y validation is the correct rotation angle in order to align this image. Then our system also will be produce some rotation angle. These are the rotation angles, as you can see, for Y validation. Some of them are positive, some of them are negative, so some of them should be rotate in the left, anti-clockwise or clockwise. Our model will be also predict some numbers as the output, and then we can compare them with the correct rotation if they are equal, or actually we can find the difference between the prediction angle and the correct angle and use some mean square value from this error as the accuracy of the system. Here we don't want to mention the correctly classified or not. For example, the first one should be rotated 37 degree in the anti-clockwise. So my system predicted as the 35. So there are 2-degree difference between the prediction value or regression value and the correct value. For the next one we have 3. For the next one we have 5. So all of these errors will be added together, then we will get a square root and divide it by the number of samples and use this number as the mean square root error, and it is the performance metrics for this type of problems. Okay, here I display some of them. Of them, and also the value of the angle that they should rotate. This is 8 and it should be rotated 28 degree, 7 with 36 degree. This is almost aligned, only 4 degree necessary. This one also 1 degree. This one needs 42 degree in the clockwise direction. This is -9, this is 10. So you can see we have images and some numerical values. Again, I declare one CNN from scratch, and this is the size of the input samples, 28 pixels by 28 pixels, and they are grayscale, so we use only one channel. Convolutional layer, batch normalization, and rectified linear average pooling. Instead of max pooling, we use average pooling here. Again, we have these batch of or these 4 layers one time here, and here we have two convolutional layers after each other, but before we put between them we should perform the rectified linear unit, of course. So till this point it is very similar. This is another layer that you can use in all of the projects. Drop layer, drop out layer. It means that in order to avoid overfitting, only we during the training and updating the weights, we ignore 20% of the weights. So each time for each image or each batch of images, 20% of the weight will be not changed, and only 80% of the weights will be trained. In order to make it in order to avoid overfitting, it is sometimes necessary. You can remove this line and see the result, and also change this value between 0 to 1, of course. So if you use 1 here, it means that you don't want to train anything, or if you put 0, it means that every weight should be trained. But now we drop out 20% of the weights, so 20% of them are not trained. In the end, we need a fully connected layer with only one neuron, and the last layer instead of classification layer is regression layer. So this is the main difference between the classification, CNN, and regression. In the last layer we have a regression, and it generates a number instead of a label. The other part is similar to the training CNN architecture. Mini batch size, maximum epoch, again initial learning rate, again we use scheduled learning rate piecewise, and in the beginning it is 0.001, and every 20, let me check it, is it iteration or epoch? It should be epoch, but every 20 epochs, so we have only 20 epochs inside 30 epochs, so one time only it is dropped. Let's see, MATLAB. Okay, number of epochs for dropping the learning rate. Okay, after each 20, in this example, epochs, so for the first 20 epochs the learning rate is 0.001, then it will be dropped by 0.1. So for the validation data we have image and the real or true angle that we should rotate. We should provide both of them. Validation frequency and plot the training progress. Let me run it till this point. I think since the size of the images are very small, this model should be trained in a few minutes, and I can show you. So this is the last function. As you can see, it is dropped, and this is the mean square error. In this in the regression problem, we expect to see the error is decreased during the progress. This is the error, so we want to find as much as possible this we want to make it as small as much as possible. So till this point the error rate is 10 degree. In the epoch 2 it is here it is 12 degree. Now it is 10 and it is still working. Now the error rate is approximately 8 degree, the average of the error rate. Okay, before I continue, and we should wait until this part is finished. You can ask your question meanwhile.
In practical example, sir, where can we use these two codes, the first one and this digit regression?
It depends on the problem. If you want to classify something, we use the previous type of the code, but in some questions the output of the result of the model should be a number, a numerical value. For example, you want to predict the age of a person. My PhD thesis, we want to train a model to predict someone's age. So the output of this system is a numerical value. For example, I upload your image into my model and it said that you are similar to someone with 25 years old. So the output is a value 25.6. But in some type of the problems, for example, you want to perform face recognition, so we want to find out who is similar to this guy, or do you know this guy, or can you identify this person or subject. So in this type of the problems the output will be a class label. Or in the image recognition, you want to recognize different objects. So in this type of the question, the output will be a label. So it depends on the nature of the problem. As you can see till this point, the mean square error is 5 degree, the average mean square error.
Sir, can you define the difference between loss and this error? Mean square
This
error.
is the loss function is a function that is declared on the architecture, and actually the value of the loss function will be used to train and update the weights of the network. So in most of the case, in the for example classification problem, let's see how can I explain it for you. Loss function in classification. Let's see first for this one. The loss function for the regression is the value that is predicted by the system, but subtracted from the actual value. So I enter one sample to the system during the training, and the system predicts one result for that one. For example, the rotation is, the actual rotation is 10, but the system predicts 20. So there are 10 value or 10 degree difference between the correct and the prediction or the output of the model. So we have 10 value error. By using this 10 value, we want to update and change the weights of the connections in the interlayer of the CNN. But in actual situation, we don't want to use one image and find the error from one image. We use a batch of images. Here we mentioned that mini batch size is equal to this value, so 128. We give 128 samples from the training set to the model. Then for each of them, the model will predict one value. We save them and find the error for each of them. Add them together, this value will be considered as loss. And as you can see in the beginning, there are, for example, 300 degree between errors between the images, but after a while it is decreased, and now it is something near to 10 or 20. So all of the 120 images that I give to the system, the amount of the error of them is 20. But for the classification, there is a formula, because we don't have numerical value for the output. So for example, I give it an image of dog, and the system predicted as an image of cat. How much is the error? Or I give it an image of airplane, and it is considered as a horse. So how much is the error here? Is the first case is worse or the second case? So there are a formula for the classification problems, but in the regression problem, the loss can be completely found out by the difference error between the prediction value and the correct value. I will display it in another part of this session. Let this part complete. It is almost finished. And the prediction rotation value in average has only 5 degree error till this point, or less than 5 degree. So we can say that the system successfully find the rotation degree for samples. Okay, it is finished. And this is the mean square error for validation set, 4.48. In average, there are 4.48 error in the predicted angle and the correct angle. Let me show you some of the samples from the test set and the result after we correct them according to our system. So for example, this 8 was good by original, but we change it to this one after we correct it. So for this one, the system is not work correctly, but for this 3, as you can see, after we rotate it by the angle that is predicted by the system, it is really aligned. This 9 is okay, this 1 is almost okay, this 6 is in the beginning it was okay and it is still okay. So as you can see, for example, this one is not correctly predicted the necessary angle, but this 4, the original was this one, and now you can see it is completely aligned. The 3 is okay, this 0 is okay. So for some of them, as you can see, for example, this 4 is completely aligned now, this 3 is almost aligned. There are some errors, of course, because the mean square error is now 4.5 degree, so there are some problems. For example, this 1 is almost aligned, but it is necessary to rotate it in the anti-clockwise 20-30 degree mode. The 9 is okay, and in this shape I show you the predicted value and the true value. So for example, the correct angle for that image is minus 40 degree. My system also predicts some of them 40 degree, but for some of them, as you can see, my system predict 30 and minus 20. For example, this one minus 25, this one minus 26, but the actual rotation degree was minus 40. For some of them, the system predict minus 41, but the actual minus 44, sorry, but the actual one is something different. So you can see there are a few degree between the prediction and the correct one. Of course, if these class are more if all of them put inside the red line, it means that there isn't any error, but for each of them we have some prediction left or right. It means that for some of them we have more the angles are greater or less than the actual angle that is given in the train set or test set actually. So for finding the error, we consider the absolute value. So if it is 5 degree less or 5 degree more, we both of them consider as 5 degree error. For example, here for this sample, the actual rotation was 15 degree, but our system predicted as 20 degree. So there are 5 degree error. Also here, for example, this one, this is the correct degree is 50, but the system predicted as 10 degree. So here we have 5 degree less, or 5, in that case we have 5 degree more than the necessary degree rotation. So for both cases we consider as 5 degree error because we find the absolute of the x and y. Let me come back to the code. So here again, for finding the prediction angle, we use the predict method, and let me run it. Prediction, sorry, I think there was another think I run it again from the beginning. No problem. So the prediction error is the difference between the correct rotation angle and the predicted value. These are the predicted value. As you can see, the system predicts some 5,000 values here, and these are the correct one. For example, for the first image, we need 37 degree. My system predict 33 degree. So there are 4 degree error here. For the second image, minus 36 is the correct rotation. We predict minus 29. So there are 6 or 7 error here again. So all of this error will be considered, and we find the absolute of them and divide them by the number of elements in order to find the accuracy. Also, we find the square root of them. So the mean square error is the square root of the errors, absolute error between the correct prediction value and the correct value. Here I display this plot, and finally by this part I display these original and corrected version. I use image rotate in order to rotate the samples of the test set according to the predicted value that is provided by my model. These two parts of this figure is provided by this part of the code. So this is the way that we can perform regression by using deep learning. You can ask your question if you have any question.